So for problem 346, we have a crate which is supported by a system of cables and springs. And what we know is at the point at which this crate was attached, due to its mass, by a gravitational force attracting it to the center of the earth, that it would place this cable connected from the origin to the hook in tension. And then that tension, in order to be in equilibrium, would be offset by the forces which are induced both in the cable along with the springs. So specifically, you can imagine when this kind of weight is connected, those springs will be stretched somewhat from their equilibrium position towards the origin. That will generate a restoring force, tending to pull them back to their equilibrium position in each of the springs. In addition, the tension in this cable will serve to pull. Really what's going on here is it's this point of connection at the origin that's hard to see in the diagram as we have it printed. And those three forces are serving to offset the weight which is borne in the tension of this cable. So the key point that you need to know in order to be able to solve this problem is that for a spring, the restoring force is proportional to the displacement. And I will use the same term that the book does in this question, which is stretch. So this just means that we'll have a restoring force. It's going to be aligned along the direction of displacement, and it's going to be proportional to the amount of displacement, where this is the spring constant, which is just a measure of stiffness of the spring, or how much energy does it store for a unit of displacement. So if in this particular example, if you notice what we're asked is the stretch of each of those springs, shouldn't be in there. It's an artifact of printing. So in order to find the stretch of each of these springs, I just need to find what the restoring force that is induced in each spring when the load is connected. So just like every problem we've worked until now, we're going to draw a free body diagram around the origin, which is this common point of connection at which each of the forces in this force system is concurrent, meaning its line of action passes through the origin. And just to reemphasize, as we move into chapter 4 for the last time, concurrent forces can be modeled as a particle system. So let's kind of draw a free body diagram, or we'll just take some of the detail that is in that original drawing and take it out. So we're modeling this point of connection as a particle. I have the weight of the object, which is translated in that cable. It goes directly in the negative z-hat direction. In addition, I have, if I kind of extend out my axes in the negative direction, I have the force, the restorative force associated with the spring connected from O to B. It's going to be directly along the negative x-axis because the restorative force always is opposite the direction of displacement. So when those stretch towards the origin, back along the axis of the spring, that will be in the negative x direction. So I'll call that FOB. I'll have FOA and a similar ideal along the negative y axis. And then finally, I can describe the tension in this cable, which serves to provide kind of the vertical component to offset the weight. It's going to be directed along the cable, which is described by a unit vector from point O to A. The easiest way to kind of sketch that out, if you really want to, is to just kind of get a point of intersection in the xy plane corresponding to the dimensions. So if you notice, you're going to come out 6 in x and over 4 in y. So not quite as much over as out. So let's just say it's like right here, and then go up 12. So just to make the math, the drawing look somewhat reasonable, I'm going to draw it like there. So that's FOC. And that looks nothing like the actual free body diagram. And that's kind of good because it shows that for these particle problems, we don't need a very accurate free body diagram in order to solve them. But that should be directed along the axis of that cable. And it's, again, if you did want to sketch it, if we had graph paper, we could draw a nice version of it. So what do we need to do? Well, if we just find the magnitude of these two restorative forces, since we know the spring constants, we can compute the displacements. How will we solve them? Well, we'll find them by enforcing our condition of equilibrium in 3 dimensions, which says that the resultant force acting upon this body, if it's in equilibrium, is 0, which means that you have your 3 scalar conditions of equilibrium, which will allow you ideally to solve for 3 unknowns. So let's decompose each of these forces. Let's begin by the weight. It's an easy one. As long as we choose our z-axis to be perpendicular to the Earth, then all weights will have no x or y component, and they will have the magnitude of weight in the negative z direction, which for a known mass you compute by multiplying by the acceleration due to gravity. Let's do the two restoring forces of the spring. Let's start with FOB. If you notice, that's directed along the negative x-axis. That is a magnitude that we don't know. However, we do know, since the axis of the spring is along the negative x-axis, that the y and z component will be 0 of that restoring force. In a similar idea, FOA has no x component. It has a y component of whatever that unknown restoring force magnitude is. Again, by our coordinate system, since this is plus and this is plus, that's in the negative y direction. So z is 0. And then the force associated with the tension in that cable is going to be a little more complicated because, yeah, we don't know the magnitude, but we can compute the direction, but it's not going to be easy as just assigning it to one of the three axes because it's off axis. It's directed along the cable. So what I need to do is first determine the coordinate location of C. And we'll notice that in order to get there, kind of again, follow the dimensions as a guide. You'll notice we go to this point in the XY plane, and then we go up. So the question is, how do you get this point in the XY plane? Well, it's positive 6 out in X. It is positive 4 out in Y. And from that point in the XY plane, it's up 12 in Z. So remember that I can always write an expression for a position vector between 2 points. The origin in C in this case is taking the coordinates of C and subtracting away the coordinates of O. But since O is the origin, that's going to be easy. The corresponding position vector will just be the coordinates of C. And I can compute the magnitude of ROC by simply taking the square root of the sum of the squares of each components. So we can compute that in a calculator. Let's do it. Square root of 36. I'll do the squares, the same typing because it's late. And I get 14. 14 what? Well, since all of those dimensions that were provided are in meters, that will be 14 meters. So what that means is if I scale my position vector by that magnitude, I will get 6 divided by 14, just cancel the common factor of 2. You'll get 3/7, 2/7, and 6/7. So what that means coming down here is I can express FOC in rectangular form by just calling it 3/7, whatever that unknown magnitude is, 2/7, whatever that unknown magnitude is, and 6/7, whatever that unknown magnitude is. So in forcing equilibrium, for my three scalar equations, if the sum of all forces in the x direction is 0, and we're kind of using the convention that that's positive x, the same axis that we've drawn, what that implies is that just take all of your x components and add them up. So it's going to be, and I'll just skip the zeros for now, minus FOB equals 3/7. Sorry, I should say plus 3/7 FOC, getting ahead of myself, equals 0. So just check that we get all the x's, no x, minus FOB, no x, 3/7 FOC. So what that's going to tell me is I kind of have a highly decoupled equation in terms of my unknowns. Remember, your three unknowns here are basically the two magnitudes of the restoring forces and the tension in that cable, because we know that the tension in this cable is just the weight. So sum of all forces equals y. That's what we're calling the positive. And if that is 0, what that means is that, again, going along our y components, we will find that minus FOA plus 2/7 FOC equals 0. So again, if we just knew FOC, we could solve for both FOB and FOA. And summing all forces in the z direction and calling that positive, we will find that minus mg equals 6/7 FOC. And that's not surprising. I should say, sorry, I keep doing that. I want to write the whole equation first before I simplify to that point. The sum of all z components, minus mg, 0, 0, and 6/7 FOC equals 0. Now what that means, and not getting ahead of myself here, we knew that this cable from the origin to C was the only support structure capable of providing a vertical component of force to offset the weight of that crate. So what that means is I can find FOC by taking mg and just multiplying by 7/6. That's the same thing as dividing by 6/7. So what will that be? Well, let's take and the mass was 25 and the acceleration due to gravity is 9.81 and 7 divided by 6. I'm going to get 286 and I'll hold all the precision for now since I'm going to compute displacement 0.125 and that is in newtons. So therefore, I can find FOA as just 2/7 FOC, and I'll go back to my .chem in a minute. But let me get all this written down. So I'll take that answer and multiply by 2/7. Then I get 81.75 newtons, and FOB is just going to be 3/7 FOC, which is just going to be, let me go back and get that, 122.625. And again, I'm carrying all the precision because I ultimately want the displacements. So let's actually do that. Remember, the displacements are only associated with the spring forces, which are FOA and FOB. So I can write, and just, we weren't asked this, but if you wanted to determine the actual direction of the displacement, when the spring is stretched in order to generate that restorative force, they're going to stretch towards the origin. So that's in both the positive y direction for OA and the positive x direction for OB. So we can just write them as delta y and delta x, and it turns out that it's a physically meaningful thing. So to get the displacements here, I would say that FOA equals KA times, and A is the one that's in the y direction, right? So that would be delta y, which means that delta y will just be FOA divided by KA. And let's get both before we go to the calculator. FOB is going to be KB times delta x, which means that delta x equals FOB divided by KB. So FOA we had is 81.75 newtons, and we're going to divide by the spring constants. We were given as 290 newtons per meter. So newtons per meter, the newtons will cancel. We'll get 1 over meters, which is just meters, as we expect. 122.625 newtons divided by 290 newtons per meter. So let's actually compute what these are now. So for the first, and we can see we're going to have to put these in engineering notation because they're going to be less than 1. If we take that 81.75 and divide by 290, that's the natural answer in meters, but converting that to millimeters, remember that in order to get, let me actually just show you all that if you want. So I'm going to just write what the answer is, and I'll tell you how I got it in a minute. 282 millimeters, and where are we at? 142.625. That is going to be to 3 sig figs, 423 millimeters. Okay, so if you don't remember how to do that conversion, and I'm sure everyone does, so it's just a refresher, but if I had 0.2819 meters, and I want to take that to millimeters, you can do the dimensional analysis approach, you can do all that stuff, but what I like to say is, okay, I want to have a millimeter. I want that. And if I want that, that really means multiplying by 10 to the minus third. But I can't just multiply by 10 to the minus third. I can only multiply by 1 and not change the value. So what I would also have to do is divide this quantity by 10 to the minus third. So what I do is I make the prefix that I need in order to get my prefix. I leave that alone, and I take the adjustment and I roll that into the coefficient. So what this becomes is 0.289 divided by 10 to the negative third times 10 to the negative third meters. So you notice this is unchanged because really I'm just multiplying by 1, 10 to the minus third over 10 to the minus third. So when you divide by 10 to the minus third, that's really multiplying by 10 to the third, which is just 1,000. So that's why this decimal just gets shifted over 3 points, and you get 289, and then rewrite 10 to the minus third as just the prefix millimeter. So that's how I was doing that conversion in that case, but I lost a 1 in there, so that's 281.9 millimeters, which is about 282 millimeters. So since I'm going to scan this, I'll write that in. This is how to convert. But we all know that once you get the conversions down, you don't think of it like that. You just know, hey, that's way too small of a number. That I should say a meter. The number is way too small, which means the meter is way too large of a unit. I need to make the unit smaller. And remember that in engineering notation, you always try to write your coefficient between 1 and 1,000. So I see in order to make that number between 1 and 1,000 and have a order of magnitude that's a multiple of 3, that I would shift 3 places. So I'm not going to be able to, in just a minute here, go over how to do those metric conversions. If you'd like me to do any more examples, though, I'm happy to. I'm just assuming that all of you have already mastered that many courses ago. But I think that's it. If you're watching these in order, that's the end of the practice exam. And let me know if I can do any other questions to make it easy for you.